here again, which you know already from this morning. So Mino will start and then Kurt take over, as far as I understand. And they are looking at lower level now. They look at IPv6, IPv4 siblings and detecting them in the internet.
So, hi everybody, my name is Mino Ruhi, and together with Kyrin Scheitle, I will be presenting this collaborative work, which also involves Oliver Gasser and Jörg Kahn. So I would like to start with the topic, with the motivation behind the topic, namely why do we study it and why this question is important. So as we all know, there is an increasing trend in the deployments of IPv6 addresses in the internet. And as the transition from IPv6 to IPv4 would be gradual and will take some time, IPv4 is still the prominent IP address of the internet and probably will stay with us for quite some time. So this is an interesting and valid question to find out to what extent IPv4 and IPv6 addresses are coexist in a dual stack manner together. And knowing this fact or this type of deployments, there are some service level insights and use cases to that. For instance, one could venture into comparing the performance of the IPv4 protocol against the performance of the IPv6 protocol, and also evaluate the security loopholes or correlated failures which might stem from such a mixture of infrastructure. Our research is based on the initial results of Beverly and Berger's research paper, where they basically answered the question or addressed the problem of identifying siblings using TCP timestamps. They define sibling as an IPv6 and IPv4 address pair which belong to the same physical machine, and this is the same notion that we use in our paper. So to answer those questions, this is the overview on our methodology. Basically, what we first do, we collect diverse and large ground truth data set which exceeds prior work. And then in the next step, we run a set of active measurements against this ground truth data set by making parallel full TCP connections to both IP protocols to every single host which is within this sibling dataset over a 10-hour period. So basically, after the end of the measurements, we have one trace for IPv4 and one trace for IPv6 for each sibling in the sibling dataset. Then in the next step, we extract multitudes of features from the measurements which are actually used in for discerning siblings, so for sibling detection. Then in the next step, we develop two different algorithms. So one is hand-tuned, and then we convert it and migrate to a machine learning algorithm which operates on the discerned features or extracted features. And at the end, we train and evaluate these algorithms based on test train splits and machine learning techniques. So here's the view on the ground truth dataset. So we first started with a ground truth dataset in March. So this is 2016, in March 2016, with around about 450 hosts. And then we extended it with more hosts in the other data sets, which is accumulated in December, with around about 700 hosts. And what is important to note here, or what I want to mention here, is that we try to generalize, to better generalize and capture a better representative of IP siblings in the internet by introducing different types of diversity in our dataset. And this diversity can be seen in the basically software and hardware versions of different sources that we took for our ground truth data set. So these are the servers that we had access to. We also used NL-NOG rings for these measurements, and also write Atlas anchors. We also compare our ground truth data sets to the one which is provided by the related work. Also, we capture geographical dispersity, meaning that our datasets covers more than 80 countries, and also administrative diversity in terms of number of autonomous systems. Also, another feature to point out in the ground truth dataset is the type of skew characteristic that we observe here, which is compared to the basically related work. It captures a more variety of skew behavior. So we also, for testing purposes, we also built a non-sibling data set with mixing IP addresses which are unrelated in terms of sibling relationship from different servers here. So at this point, then we have our ground truth data sets, and we have also conducted our active measurement techniques on the ground truth, and we have the results. And as the basically detection technique is a skew, clock skew based detection technique based on TCP timestamp, I would like to clarify some terminologies in the first place before going into feature extraction. So a feature in general can be falsifying, meaning that it can eliminate a non-sibling relationship, or verifying, meaning that it can discern a sibling with basically a certain level of certainty or with confidence. Then there are two related terminologies which are based on clock skew inference. So the first one is the clock offset, and this is the time difference between the remote clock, so basically the targets that we are probing, and the reference clock, which is the basically notion of time of our prober. And this is computed by getting the TCP timestamp and also the receive timestamp from the packets that we get back from the probe. Then we compute the skew, which is the frequency difference between the targets and the reference clock, and it's the first derivative of the offset points. So here's the terminology. Then we have, so I have listed some important features. There are much more detailed to the feature part and much more features that I can explain, but just for the sake of brevity, I have listed these ones. So the first one is the TCP options fingerprints. What we check here is the presence and order of TCP options. And if there is a window scale option, then we also take the value for IPv6 and IPv4. And this would be the first filtering point, basically for comparison of siblings. And the important thing to note here is that this is only a falsifying metric, or can be regarded as one, because the number of operating systems which are available out there, and as a result, the TCP options fingerprints are lower than the number of existing hosts out there. So there could be clashes. So that's why this is only used as a falsifying metric. Then coming to the next prominent feature is the raw TCP timestamp, and here basically the delta between the raw TCP timestamp of IPv4 and IPv6, or the probes, the packets that we received, are compared. And as TCP timestamps is a 32-bit basically value, which is monotonically increasing, this provides a certain level of entropy over host. And for a sibling, then we expect the difference to lie within a very close range, because they are expected to be generated from the same host. And this is strong indicator, or very high, has very high discriminative power in terms of verifying siblings. And there are multitudes of features which are obtained as basically the results of computing clock offsets and computing also clock skews, which I will not go into detail here. But what I would like to show here are these interesting graphs. So here on the x-axis you can see the measurement time, so this is the prober time, and on the y-axis you can see the observed offset, so the difference between the clock of the prober and the clock of the remote host. And so this is these are all sibling pairs, and what we can observe here are different types of skew characteristics that we can observe in the ground truth dataset. So the first one is a negligible skew. So as you can see that the first derivative of the offsets is almost zero, so the clock is very stable here. And so in this graph you can see a constant skew for a sibling. And by the way, so we have two traces, one for IPv4 and one for IPv6. And so in this graph you can see a sibling which demonstrates variable clock skew. And also this is an interesting case of a clock reset for a host. So as you can see, the notion of time here is being reset every hour or so. And the algorithm has different features and different mechanisms to identify different types of skew and accordingly classify them in the decision algorithm. So I would like to show an example of variable clock skew and what feature and basically method is used to classify. So this is a sibling pair, or this is a sibling with IPv4 and IPv6. So we have this offset trends, and what we do here is that to capture the trends of the skew, we fit a polynomial of degree 3 on the offset points, and then we compare these two graphs in terms of similarity, which is basically here the distance between different points of these two trends. And here is an example of a non-sibling, and as you can see, the trends, or the skew trends for IPv4 and IPv6 are obviously different, and basically the algorithm then is able to detect that and classify it as a non-sibling. Yeah, so this was from my part, and now I will hand over to Kyrin to continue.
Thank you. Good. So I'll take you through the two different algorithms that we applied. One, the manually tuned, and the other, the machine learned algorithm, which is basically a decision tree. So we started out with the manual algorithm and said what features do we have and what do we believe will work and in which order should we apply. And we tuned it to the extracted features, and we used it on the kind of older, smaller data set as a test data set, and then as a train data set, and then tested it on the later, bigger data set, excluding the previous hosts. Basically what it does, it falsifies all the pairs where the TCP option signatures are different, so there we get rid of non-siblings as a first step. Then we falsify based on the raw TCP timestamp evaluation, which is one of the features before, and then we look into the skew classes and say, is it linear, or are they both negligible, then we can't tell anything, or are they both variable, and then we apply the polynomial spline matching and look into that. The algorithm has a lot more details, and it showed a good performance, so we'll show the performance metrics later, but it performed really well, but we realized it has 20 decision points and 10 parameters, so it was just, you cannot like do a cross-validation on it, you cannot retrain it all the time. It is difficult to adapt to a new ground truth, so we said, let's look into, can we apply machine learning to actually train a good classifier and replace this well-functioning but complex and hard to train algorithm with something automatic. And we started with the most basic thing, a decision tree, and we do all the tenfold cross-validation, different train test splits, all the subgroups. Yeah, so we make sure that we don't overfit on Web Atlas nodes or something else. And we use Matthew cross-correlation as a metric to compare, because it is difficult if you take all the precision, accuracy, recall, and all these things to compare across algorithms. And MCC nicely factors in all these into kind of one number that you can compare. And if we look at the results, we see that the Hessian-tuned algorithm performed really well, and both train and test error were really low. So it means we need an underfit and likely generalize as well. And machine learning basically achieves the same performance. But then the interesting thing is, don't treat this machine learning as a black box. Look into what did it do. And if you have a decision tree, you can print it. It's really nice. And we looked into it, and it just used one feature alone to replace all these 20 steps and 10 parameters. And the feature in case were the raw TCP timestamp. So basically the entropy of where is this 32-bit value, which correlates to host uptime for most. And actually you can, at least for that ground truth data set, perfectly fine, just match on that value. Say if it's very close to each other, you can verify on it. So we were really surprised that it could also work that easily. And I think these kind of stand next to each other, and we'll come later to which one you should probably apply in which scenario. Then an interesting thing that occurred during our measurement, we measured the leap second end of last year. And if you look at the RFC, the TCP timestamp clock, it should not do anything. It should just continuously tick on forever without any interference from anything. But this was the leap second, and then this was the time when it happened. 1 hour later, apparently some NTP date command kicked in, adjusted the time, overshoot, and then 1 hour later corrected it back again. And there are some of these funny examples in the paper as well, which I think, I remember your talk on TMA last year, NTP and time in the internet is still a mess today. And here's another very interesting thing. So very recently, after we had finished the paper, Linux actually integrated a patch to randomize TCP timestamps based on source IP and destination IP total. What does that mean for us? They did it for reasons to, for example, stop net device enumeration. So there was a paper earlier on that you can use timestamps to enumerate devices behind a network address translation device. So that is one of the reasons, and also uptime estimation. There are some blog posts in the internet that say, disable TCP timestamps, people can guess your uptime. I think that's a bad idea, but that was one of the reasons why they included it into the kernel. And basically, these raw TCP timestamp methods that the machine learning nicely found will not work in these versions anymore. But the long-term Skew-based measurements will still work perfectly fine. And the good news also is this will be in the 4.10 kernel. The new Debian version is 4.9, so I guess we have some while. So if you want to do something using that, do it in the next 1 or 2 years. Good, and that also brings us to future work, right? We wanted to reduce that measurement time, and we are very close to having an algorithm that just does it on one packet. We achieve very good performance on one packet. We can identify and classify sibling candidates based on passive observations, where we don't know anything, just see traffic passing by and then pick up likely siblings. We will look closer at the Linux patch impact, and also if you have more ground truth hosts, please do a pull request on GitHub. It would be really nice to get more of those. Good. That's the end of our talk. Thank you for your patience. We'll be happy to accept questions.
So before I accept questions, I actually probably should give you some information that this patch is your own fault. Because you presented this work as a meeting, and Florian Westphal, who saw this talk and the discussion about this talk, said to me, like, he already has a patch, he can submit it. And I was like, yeah, go for it. So it's your own impact here. But at least there's impact, right?
He also told me about the patch. Okay. Discussed with me.
So now we go for questions here.
Yeah. So what you're trying to do is the sibling analysis, and what you get is pairs for end hosts, right? How much of this methodology can be applied to find siblings in terms of router interfaces?
Mm-hmm. So we've been thinking about that, and you need routers with open TCP ports, which might be SSH, BGP, or something else. which people typically get annoyed if you scan them. And you would, depending on the methodology you apply, if you scan for 10 hours, I have ethical concerns actually applying it to routers, because I think it might not be conceived as nice.
I know you mentioned it. So what was the motivation? Like now you've mapped what's the V6 address my phone's using versus the V4, and probably like my home router. That's the device that has both IPs, and that's something that you will detect because my device is behind the NAT. What's the motivation? How is this data helping others?
So I think similar to the previous work, we also did this large-scale scan, and I think that's where you can go further to figure out which services by which content providers are hosted on the same servers for both protocols, which entities in the internet use an IPv6 proxy or something like that. I think in those areas you can safely apply it.
Yeah, but this is, you will get a mapping of what my provider decided to allocate me. So what's the /64 that's being used at my home, and the V4 address that I have. How is that correlated to the content that I will access over V6? Because I could access some parts of a web page over V6 and then some ads because the ad network is not serving over V6, then that's something I'll fetch over V4. So you know that there's easy ways to know what's the client. This client is talking to me over two different stacks. But how is that helping either the provider in terms of content delivery or the transit guy, and how should they be using this information to route the traffic differently?
I've not thought into that direction
Okay,
yet.
no, I'm just curious, and we can take this offline.
Yeah.
This is fascinating. Good talk.
So I think this is actually a good contribution about evaluating the state of transition between IPv4 and IPv6.
Yes, for sure.
So yeah. So
Oh, yeah, and also quick question. Did you find cases where the V4 address, once you have the mapping, was embedded in V6 and you could see that?
We did not look for that, but the previous work did find such cases, so they exist. Yeah.
I have another question. So, did you try to do like OS fingerprinting in parallel and try to correlate if like some OS are working better than others and stuff like this?
Yeah, we looked at all the stuff that Nmap does into the OS fingerprinting, and we did not implement it because we did not find it conclusive in small samples, and also it has quite some overhead in measuring. I mean, Nmap does all these funny things of sending quite a lot of packets. So we did not find it helpful to actually map it to operating system versions or flavors.
If you run this against different virtual hosts on the same physical machine, will it confuse them because the clock skew is similar, or what will it do?
Yeah, that will be interesting. So basically, if you have virtual machines or even servers in the same rack, you might get funny cases. There was a paper in, I believe, SMP or something, where they used a similar technique to identify Tor hidden services. They say, we heat up one server, generating load, and the server on top of it will change its clock behavior. So it does influence each other.
Just for curiosity, so you are trying to match an IPv4 with an IPv6, right? How you choose the pairs?
So for the ground truth, we
For the ground,
we knew.
okay.
Yeah,
But
for
say-
the large scale scan, we did DNS resolutions and got A and quad A records. And then for domain matched, we built all possible combinations to form candidates.
Okay, but you don't know. You made multiple matches there.
Yeah, because if you get 4 A records for quad A, everything could be possible.
So I'm not a specialist of NTP. Is it possible to have a skew on your NTP server that affects several hosts around, and then you can see this skew
So
propagating
you
from
say
the server to like everybody that is actually using the server?
I guess, yeah. So I guess if you have an NTPD daemon in your network that has some characteristic and all your servers are synced to that, and that characteristic seeds into the clients. Is that your question?
Yeah, maybe you can infer the infrastructure like from different hosts that have the same skew, the same kind of change.
We did not look into which NTP server they were synced to, but if you take that one more step, you could, yeah.
But when you look at the skew, it's on a very short time scale. The graph you had, it's like many samples in a few seconds. And I guess like the host won't be synchronizing that.
No, we did 10 hours.
10 hours.
Oh, okay.
So to get some, you need multiple hours to have actual real skew observations.
So you reach a very high accuracy with it, but it's also rather complex, right? Did you look at maybe simpler approaches, just looking at the minimum round time or whatever, and how much the accuracy would be there, like for comparison purposes?
Which minimum?
Minimum round time, maybe?
I
don't know.
think we did.
look
Yeah.
into that in the beginning, but the accuracy was really, really low, so there was no indicative
Okay.
sibling.
So we looked at all these, I think TTL, round trip time, and whatnot, and
Hop counts and
yeah. But it all had very bad metrics.
Okay.
For
So
all
it's
these.
not even like for first classifications, W was just like unusable, you say?
I think we also had many siblings that just had different hop counts, and then you already have a lot of false negatives.
So that means like IPv4 and IPv6 might be differently routed then.
yeah.
Yes,
Okay. Interesting.
definitely.
And that's actually also something interesting to look at.
Yeah.
Yeah, okay. Final question for today. Anybody wants to take that on? No? Okay, then thank you very much. Do you have any announcements, or like I can just ignore you?
We have no special announcements now. Everybody is free for the evening. If you're looking for somewhere to eat, there are loads of places on Maynooth Main Street. Go and investigate and pick a nice one. Maynooth has recently been awarded a purple flag, which I'm sure nobody has heard of. So it's like blue flags for beaches, except it's supposed to be a safe place for nightlife. So it should be safe to go out in town in the evening and enjoy the pubs and enjoy the restaurant. So we're back here in the morning, and I'll see you all there.